Good morning. Thank you all for coming. My name is Mark Knutson. I work for Keysight. I'm a PSS solution engineer. I get to work with a lot of great customers like you guys. And I'm on the simulation side, and I get the distinct pleasure to present to you today an interesting paper, kind of an Oreo. There's some good cream in the middle, but you're going to get a digital twin side, and then you're going to see Trust But Verify. My partner, Dustin Brown, and I are going to present to you. I'm going to present a digital twin on the front side, and he's going to present on the back side, validating it with measurement. And you got to turn that on. So it's going to be a two-parter where I'm going to cover that simulation side and kind of look at what a digital twin is. There's a lot of different definitions out there, so we'll check our terms, make sure we're clear on that. And I'm going to actually show you a real digital twin that we built with COTS parts with analog devices. Some of this was presented at IMS, the last IMS in San Diego. And I think you're going to see a pretty interesting way that this is presented, a very high fidelity model. And we're going to look at the keys to have a high fidelity model, and I'll go through that. And we're going to check measured versus simulated. And then I'm going to hand it over to Dustin, my partner, and he's going to look at it from actually validating it, measuring it in the range. So I always like to start with the Baked Alaska. If this was a cooking show, I want to start with the Baked Alaska. It's just already came out of the oven. It's just perfect. So this is where we're going. We're going to build up a digital twin model that actually validates and we can measure it. So at bore site, plus or minus 30 degrees off, we can look at different full array, subarray, and we can look gain. We can look noise spectral density, which you could calculate G over T. This is a receiver. And we're going to look at IP3. And this model that we're going to show you how we built that up, we can even introduce things like variation in phase between the elements or the feed lines or a number of different parameters like that. And you can see that. If you zoom in on this, it's hard to see on this, but there's a blue trace, and that's measured from ADI. And the red was what our SystemVue software, our PathWave design software, predicted, right, with phase variance. And so we're going to show how we build that up. In terms of, let's check terms. Let's check terms. Digital systems engineering, digital twins, what do I mean by that? What I mean by that is that if we can marry a process into our design flow from concept, design, prototype, manufacture to test, that is where the predictive money is, right? I just dropped off my daughter to our oldest child to college, and now she's dealing with all the roommate stuff of interactions at her college, and I'm like, I wish I had a digital twin to predict how she could have the best path to friends. Well, if we can actually do that with space design, the power there is immense, as Sandeep was speaking to. Design to market, saving money, lower spins. And if we can up the accuracy, so you hear a lot of shift left, well, we're shifting up. We're going to shift up the accuracy on the throughout this design flow process on the predictability, the confidence that we have in that model. There's a lot of different digital twin, MBSE, model-based system engineering. You're going to hear these digital mission engineering. There's some good quotes there on what digital twin is. In my mind, my customers call it a surprise killer. Surprise kills me, so if I can have a way to predict something before I have a surprise in my design flow, that's good. And so it's mimicking something. I like the middle definition. It's mimicking something in how it's going to behave in the harsh environment it's going to operate. If we can predict that, hallelujah, right? So in terms of the simulation side, I would say there's three killer things that we need to be able to do well to make a good digital twin. On the modeling side, it's very important. You know, it goes back to the crap in, crap out. So if we can bring in real measured data for coupling effects and antenna element patterns, how the beam's going to behave in the far field, nonlinear effects like a PA and compression on a big, huge array, if we can predict how that's going to behave on harmonically in space with temperature across the cascade, wow, that's important. And we're going to zoom in on this in a little bit. We're going to actually look at, this is the real setup from ADI, and we're going to show how we modeled that with SystemVue at Keysight Pathway SystemVue. So, and this will be modeling from baseband to RF, up channel, down, you know, the channel, uplink, downlink, transmitter, receiver, and into the baseband, into the FPGA. So the second thing would be you have to have a simulation technology that is accurate and offers you choices in the time domain, the frequency domain, and mixes them together for you. You don't have to do all your Laplace transforms and everything. You have a set of tools or simulators that do what you need to do. Data flow is going to do the time domain, so you can bring in modulated signals. The linear S, that's like S parameters. Phased array is, and so RF system is actually, we're going to get into that in a sec. It's a frequency domain simulator. And phased array is like a multiplex version of that that allows you to do huge arrays, thousands of element arrays if you want. And then speed, right? You guys have a real job to do. You don't want to sit there and babysit your simulation tool. So you need something that has high performance computing, HPC. You need something that can simulate something with thousands of elements and a bunch of S parameters describing the coupling effects and huge amount of element patterns, whether you measured them in the range or you simulated them in your favorite EM simulator. You need something that can simulate all that and do it very quickly. This is kind of walking you through a little bit on the workflow. So you are going to have typically a setup like this, right? Where you have baseband, you have the transmitter, you have some sort of front-end electronics, you have a transmitter phase array or an antenna, you have a channel, a dynamic channel with multiple things going on in there. Maybe it's a digital mission, maybe you got interference going on in there. You've got a received array antenna, and then you've got the receiver. And each of these blocks, they're all in this gray block because SystemVue can model that. Now you can start out with parameterized models. If you don't have any data, you can start out with, I have data sheet data that's frequency dependent, a power amplifier, for example, or a mixer. I can bring that in and actually simulate that. Or I can bring in measured data if I have that. You can up the ante on your accuracy as you want, but you can start out if you don't have anything. We have the pieces to put in there. So on the transmit side, you could bring your own IQ modulated signal if you want. We can use Signal Studio, which is a Keysight product that goes in a lot of our ARBs, and it'll generate spec-driven modulation sources like DVB, S2X, QAM sources, 5G NTR, 5G NT, NTN, and you could use MATLAB. There's a variety it's very open, so you can bring in your modulation sources however you want. You can also basically bring in measured data for some of the parts in your front end of your transmitter. You can measure that, hopefully use the Keysight gear. You don't have to, it can come from anywhere. You could bring in real simulated effects, so a power amplifier, an antenna, a coupling of a board, right? So maybe some oscillation on a board or coupling on a board is killing you. You can model that and bring that in. We're going to get into this, but we can definitely physically model the antenna. We have a tool for that in Keysight, but we can work with many partners. ANSYS has a great tool. And HFSS, you could bring that in. You can get, on the transmit side, EIRP. You can predict that very accurately. You can bring in, for the channel, again, you could start out with SystemVue offers some kind of basic channel models with gain and loss of the antennas, fading, but you could bring in more sophisticated models like STK can model the kinematics. We directly plug into ANSYS STK, and that can handle kinematics, and if you guys come by the demo table, we'll show you that. But like a really sophisticated scenario, a LEO orbit, satellite uplink, downlink with an interference, and we can show you that. PropSim is an emulator that Keysight makes that can also model the channel. SystemVue can take that model for the channel as well. So last but not least, you can model the receiver. We have building blocks to build one, or we even have things like the VSA software, which is in all of our instruments, scopes, VSA receivers, and you can actually measure the EVM, the occupied power, and that kind of stuff. You can even do, it's end-to-end, so you can do bit error rate through the system. G over T for all you receiver guys. And then moving along, I would say there's 3 pillars of what the system tool that we offer, SystemVue, has to offer that really make this design flow nice for you to up the ante on that on the fidelity of your digital twin. One would be what we call RF system, or SpectraSys, sometimes we call it that. That gives you, at any node in your system, spectral content at any node, and it automatically calculates the cascade analysis on your line budget or bent pipe or whatever you're doing. So at any node, it'll tell you how much gain, noise figure, compression, noise behavior, all throughout the system, and the spectrum at each node. So, and that'll help you with things like spurious analysis, troubleshooting, and even things like spectral emissions mask. I had a customer that was going to the FCC with a raft of spreadsheets to prove how their system behaved, their phase array system behaved, and stayed within a spectral emissions mask. This tool will help you do that and with what ifs, and keep you within, and even generate a nice clean report, not a raft of spreadsheets. Second up would be the phase array simulator. That is the multiplex version of this. It's a frequency domain simulator, but it's got like 7 super parts, which I'll get into in a sec here, that multiplexes across a phase array. So there's no limit on the amount of elements. You could bring in real antenna pattern data, you could bring in real measured data, and it'll do transmit receivers, so it'll do couplers, it'll do splitters. You can do custom mapping, and it keeps it really nice and clean like this, so you don't have lines, 1,000 lines going to nowhere. And it'll predict very accurately even harmonics, injecting different angles of arrival, and different harmonics and different things on the system. Last but not least is data flow. That is a time domain tool, and the value of that is it handles the kinematics, it handles modulation. So I can connect SystemVue with STK, and I can connect it with and analyze bits in, bits out on a modulated system, packages. Even look at things like protocol stack with Exata, which Mark Lombardi will talk about. Let me move on to what I think is, this is one of the things that I love to share the most is, you guys can still hear me okay? Yeah. Okay. I love to show this because it really, it turns on some lights for a lot of people that haven't seen it before. But this is the digital twin, the X-band pulsed radar system built with COTS parts from analog devices that a team from Keysight and a team from these great guys at ADI did in June at IMS. And it was using, for example, like the ATR 1000 beamformer IC. It has 4 transmit, 4 receive beamformer ICs. And their ADT 1107, that's a TR module. So they put that in an eval board. And we did a digital twin model of that from their, what they call their Stingray phase array, all the way through up and down converters, muxing, down to the FPGA. And all of this was COTS parts, and all of this was modeled in SystemVue. And what they did is, this is actually from the ATR 1000 beamformer data sheet. And they basically, everything in pink there is a beamformer IC physical path. And they basically took the S parameter, the frequency-dependent data from the data sheet, and just put it right into SystemVue, into the model, the SpectraSys model, the phase array model. And we built a very accurate model just from a data sheet. And so it could have been measured data, right? It could have been your measured data. So it opens the possibilities of that fidelity. I keep saying fidelity, and I mean it. So there's other things we did, just to kind of round this slide out. We actually had to do kind of a calibration because the ADI board had different feed length paths for each of the beamformer ICs. They were at different phases. So we had to actually calibrate, do an EM model extraction of that and calibrate it to itself. So there was one kind of master phase and then calibrate the others to it. So once we did that, we got basically a perfect match to what they were saying and what ADI was measuring in their chamber. But yeah, I hope you see that and you're like, oh, that's cool. And if you want to see this example, come by the table at the break or later today. I'd love to show it to you firsthand. I'm going to stay on time so Dustin doesn't come up here and club me with a stick like he usually does. But I got a few more slides, and I want to just kind of bring this home on the digital twin simulation side. So this is the top level design for our receiver, our X-band receiver, using COTS parts, COTS data from ADI. And what we did is, right now we're doing a plane wave, just an oscillator, plane wave, but we could have put a modulated source there. Could have put a DVB S2X or 5G NT, modulated waveform. I can control the angle of arrival, right? And then I have an antenna model. This is kind of an analog level antenna model. This is a hybrid beamformer, so we're doing analog beamforming and digital beamforming. On the analog beamforming side, we have a model here. It'll take in real, and I'll get into this in a couple slides, but it'll take in real EM simulated data from ADS, from HFSS, or even range data from your far field measurement in your antenna range or a compact range. And you could put that data in there per element. There's a lot of configurations, and even a coupling matrix, which we'll get into. So it's very accurately modeling the antenna. And then we can even model things like with S parameters and mutual coupling. And then this is a frequency domain subcircuit. So what that is this is a time domain simulation because we're looking at modulation and kinematic change. But basically, this is a subcircuit that if you push into it in SystemVue, it's a frequency domain simulation of our whole design. And I'll show you that in a sec. But SystemVue does the correlation, translates everything from this frequency domain into the time domain. You don't even have to worry about it. So there's no loss of workflow. And then there's digital beamforming. And we control the direction of the beam weights and everything. This was actually for ADI. They used their ADC, and we had a MATLAB model. We just plugged it in to model their ADC. So that's it in a very high-level nutshell. Oh yeah, there it is. So if we push into this is the full frequency domain model. And there's a lot in here. So different switching paths. There's even things like a bunch of combiners. Like a lot of our customers model huge arrays with 300 S5P couple, S parameter blocks to model a combiner. So they build a huge combiner. So it's a real physical model. I'm going to focus on the antenna, but there's really 5 other keys to do an accurate digital twin model. The digital phase shifter, the digital attenuator, the amplifier, the S parameters to bring in, and the splitter combiner. We can model all of those. Those are in this block here. We can model all of those using very realistic techniques. So the phase shifter can handle quantization. It can have S parameters for each state of the phase shifter. And you can just give it a raft of S parameter files from the vendor if it's ADI, or you can measure it yourself, and it'll handle those shifts of the phase shifter with the S parameters. It knows you're at this state, you're at this phase shift state. This is the actual phase delay. So we can do phase shifters. We can also do time delay lines. A lot of our customers are doing that. Sometimes that's a cheaper option. We can model that. I'll just move on. The attenuator also can do quantization and S parameters for different states, the digital attenuator. The amplifiers. A huge thing now with these phase array systems is as you're blasting an array or a feed line or an active amplifier in an array, where you're scanning the beam changes on where the load changes, right, based upon where you scan it. So this tool can take X parameters, some other models that Keysight has, like the dynamic gain model that you can measure on a PNA, and it actually takes load pull effects of an amplifier and can reflect those at the system level. And then I guess the S parameters, I already mentioned that. And so now let's focus on the sixth one, which is the antenna. So just to give you some context, the antenna, the way it works is, so I mentioned this before, but let me just reiterate that you can measure it in an EM solver, a full wave EM solver. Keysight has RF Pro, it has EM Pro. HFSS is another good one. There's a lot out there. So whatever your favorite EM simulator is, you can model your antenna and all of the elements and the coupling matrix in your EM simulator. Or you could measure it in antenna range. SystemVue doesn't care. It could be a compact range. SystemVue doesn't care. But if it's, the way it works if you do it in an EM simulator is you give it embedded pattern files. So it could be per element or one, if you assume it's one across them. But the advantage of this is you can handle the fringe effects on the outside if you have accurate element patterns for each element across your array. It could be a huge array. It could be 2,048 elements. And then you have to have an S matrix of how, if there's no coupling between the elements, you don't really care, but a lot of our customers care because they're doing multiple beams, multiple different architectures, and so basically they need to understand that coupling effect. So that is, you import those files and basically into SystemVue, and that's the way it looks. And you can even map, if you have custom mapping elements to paths, so it handles that. You don't have wires everywhere. It maps the element to the path through if it's a receiver, through the different combiner paths. It handles all of that. And then this is my second to the last slide, but this on the left is what SystemVue predicted using that on this ADI system, using this COTS X-band receiver, radar pulse receiver. This is what SystemVue predicted, and this is what RF Pro, which is our ADS, is our physical EM solver. I think we tried HFS as well, and it was an exact match. So that is powerful to be able to do with a digital twin. And I showed this slide at the beginning, my Baked Alaska slide. So yeah, I got a couple minutes for questions, and I'll hand it off to Dustin. He's my trust and verify guy. I'm just the simulation guy, but you can believe me because Justin's going to show you trust but verify that he measured this in a compact range. But yeah, I don't know what your reactions is to this, but it's very good correlation, right? Very, very, very good correlation. So I hope I've given you something today to like, oh yeah, that's cool. I could use that. I need more accuracy earlier in my flow. So, thank you.
Thank you, Mark, for the introduction. As Mark said, my name is Dustin Brown. I'm an application development engineer at Keysight based in Santa Rosa. And as he said, I focused on the trust but verify part of this workflow, which is the measurement and the calibration of the phased arrays. So Mark just gave a great overview of what SystemVue is capable of and the value added from having a high-fidelity model to simulate early on in your design workflow. This can help get you to a working prototype that meets your specs in fewer design iterations. saving time and money, and then ultimately going into mass manufacturing with a high degree of confidence that you're going to have high yield and that your arrays will again meet the specifications. Even with that, it's necessary to, of course, verify. Until we measure, we don't truly know what the performance of the phased array will be. So that is a critical next stage in this design and verification workflow. And I'd like to now transition to that stage and describe to you the value that you can get from using Keysight test instruments and software to calibrate your phased arrays, to measure them, to validate that the performance matches your expectations. So I think there are kind of four main reasons for why I think we have a lot of value to add to your measurement and calibration workflow. The first point is that your unique phased array hardware becomes a critical part of our test system. We actually have the ability to integrate a digital array controller. We have a programmable FPGA that we use as a default controller, but we can also integrate with your whatever hardware you're using, so that we can adjust the beamformer gain and phase states, steer the beam, iterate through calibration sequences very quickly, and that's part of the complete test system that we have. The second point is that allows us to calibrate very quickly. You couple that high-speed digital array controller integration with some measurement techniques that we've patented, which we call array leakage mitigation, which allows us to calibrate element by element in a compact test range at very high speeds. We can calibrate close to 1,000 elements per second, and that's significantly faster than some of the traditional near-field scanning techniques where you need to park and probe at over each element. We have a stationary feed in our CATR chamber, so we can do this very quickly. The third point is that our network analyzers are very versatile tools, and we have a lot of software options that you can package with those. So of course, the most fundamental measurement is S parameters. We can give you your normalized beam patterns, so you can look at scan loss as you scan a beam out to 60 degrees. And we can look at power and EIRP, but we can also do a lot more than that. I believe Mark mentioned G over T earlier. We have the ability to do noise figure measurements on our network analyzers with a cold source method, so we can measure gain over temperature for receive antennas. And we can couple this test system with a modulated signal source such as a VXGC, which allows us to do modulation distortion measurements such as EVM and ACPR. So there's a lot of versatility in using our network analyzer as one of the core instruments of your test system. And then the fourth point is that we have a variety of calibration standards that we can use to ensure that you're getting an accurate measurement, starting with our standard gain horn antennas, which are calibrated, and other references such as our eCal modules, our noise sources. We have a variety of tools that you can use to make sure that you're getting accurate measurements from your chamber. So with that, I'd like to start with a high-level overview of what our phased array test solution looks like. It starts with our software. We have a general antenna measurement toolset application with this S7601A number, and an additional option that you can add, which allows for integration of that digital phased array controller that I mentioned. Our default controller that we're using is the M9195B, which is a Pixie chassis card with a digital I/O that has 16 channels. And this is one that we've been testing and using. But as I said before, if you have an array controller, a programmable FPGA, an Arduino DUI that you're using, we can integrate with those platforms as well. And we have some experience with different digital control modules. But the software controls that, as well as the CATR chamber positioner, which moves the phased array under test. And the array controller also has a triggering interface to the network analyzer, so that as we iterate through several beam states, for example, we can trigger the network analyzer quickly to capture data, and that allows us to get data from our measurements much faster. And I'll show you some examples of beam pattern measurements in a few moments here. Finally, we have DC power supplies usually required to provide power to the array board, to the beamformer chips, as well as oftentimes cooling fans and other temperature control mechanisms. And if we need to do modulation measurements, then we can add a VXGC or another modulated source, measure that at one of our reference receivers on the network analyzer, and then get a good measurement of the distortion added from our phased array under test. The last part of the test system is, of course, the range itself. And Keysight has a portfolio of compact antenna test ranges that cover frequencies from 1 to 110 gigahertz. We have custom solutions where we can provide quiet zones up to 150 centimeters and a variety of positioner options, including high torque positioners that can maintain DUT weights up to 12 kilograms. We also have thermal control chambers, as shown in this image on the bottom, which has a very low loss and can adjust the temperature from a range of minus 40 to 100 degrees Celsius. So if you need to look at the the beamforming performance over that temperature range, or develop a set of calibration files over that temperature range, you have that option as well. But what I really want to highlight here is the quiet zone performance of our CATRs. This is an F9650A model, so it operates from 6 to 110 gigahertz, and I believe there are several quiet zone options from 35 to 55 centimeters. And what you see in this plot on the right is data that was collected from a transverse scan of a broadband gain horn across a 25 centimeter cross section of that quiet zone. And what you can see is that the phase variation is quite low. It's about 3.54 degrees, and the power variation is about 0.83 dBm over this 25 centimeter cross section. So it's not the complete quiet zone dimension, but a large portion of it. And this is what allows us to get very accurate gain and phase measurements of individual element channels at bore site when we calibrate the array. And it allows us to do these far field measurements in a reduced volume. So I believe this chamber has a reflector focal length of about 1 meter, and the chamber length is maybe 2 to 3 meters. And that's significantly less than 2D squared over lambda if you have a large array. So we have a lot of advantage from the lower path loss in this system, as well as the really low variation in the gain and phase across the quiet zone dimension. Before we do any measurements, we of course need to calibrate the chamber. When we add in the network analyzer, the reference planes start at the ports, and we need to move those to the test ports of our phased array under test and the the feed horn antenna in our compact range. So as I said, we provide a variety of cal standards and ecal modules that can be used to bring the reference planes to those test ports, eliminate cable losses. But we also are going to be developing a GUI that can be used to guide you through the process of calibrating out the what we call the range loss, which is the combination of that over-the-air path loss from the feed to the reflector in the compact range, plus the gain of the feed antenna. That's not something that we know when we start our measurement. So we need to measure it with a calibrated reference antenna, such as a standard gain horn. And we can use our CalPlane manager to embed an S2P file with the gain and the reflection coefficient for that antenna. And with that, we can calibrate out this range loss so that what you're actually measuring is the gain of your antenna under test. And that's a critical first step to doing these phased array measurements. So I want to also address the phased array controller, right? That was one of the key components in the block diagram I showed before. And this is an example of a Skippy command. So we actually couple this array controller with a Skippy interface for a generic phased array that makes the control of that array similar to what you have with our other test instruments, such as our network analyzers, right? You can send Skippy commands to set the frequency span on an S parameter measurement. And in a similar way, you can now send Skippy commands directly to your phased array under test to set the gain and phase of all of the individual element channels. So this is one example where we actually designate a specific path through the beamforming IC. And we know that there are a variety of beamforming ICs out there on the market, so we're doing our best to accommodate a variety of topologies. On the left here, you see an example of a beamforming IC that's connected to dual polarized feed antennas and has two separate beams on two separate Wilkinson power dividers that are routed through the IC. And on the right-hand side, you can see another example of a beamforming IC that is both transmit and receive, so you have a switch path, And in this case, it's single polarized, so you have 4 elements with a single feed point at each element. And with this, the Skippy command, you can actually designate that path through the IC using what we call emission, beam, and then the polarization. So that gives you one unique path through that beamforming IC channel that you can calibrate. And with that designated, you can then set the element phase DAC values. And if you sent this Skippy command to the array and then sent the apply command, you could steer the beam, for example, to a particular angle. So these are the types of low-level commands that we want to provide to give you a lot of flexibility in terms of how you can control your phased array. All right, so with that, this is an example of a proto version of our test GUI. It's still in development, but you can see here a setup page for a phased array under test. And we can specify the number of elements in each row and column if we have a rectangular array, as well as the bit resolution for the phase and the gain control of the beamforming IC channels. And you can specify the path options through that IC, as I just mentioned, so that you're aware of all the unique RF paths that you can potentially calibrate in your beamformers. And then at setup, we also have the ability to read the status. We do a status check that allows you to see, before you do your measurement, can you at least read and write SPI commands to those beamforming ICs, for example. And finally, if you have a temperature readout for that chip, we can also read back the temperature of each channel in each IC. And that way you have some confidence that your phased array is working. You can at least send commands to the array before you continue with your measurements. With that, I'd like to now discuss how we calibrate our array and some of the techniques that we've patented to do this in a compact test range environment. So the key technique we've developed is what we call array leakage mitigation. So when you turn on all of the beamforming ICs, there's some temperature variation that happens over time. So we found that we don't want to actually turn off all of the ICs and then measure one element channel at a time, because when we're operating the fully active array, all of the ICs would be on, and there's some phase drift over temperature that occurs there. So what we do is we have all the ICs on, and we can measure the individual element channels by removing the leakage effect, which is applying maximum attenuation to the other elements so that we can try to isolate the one element under test, but we still have some measured power that corrupts the measurement. That's kind of this residual power that's being radiated from the other elements. So we have some techniques we've developed to correct for that effect, and that point is illustrated here. This is what we call a phase rotation. So I'm looking at one element channel and I'm iterating through all 64 states in this case, because we have a 6-bit phase shifter. And what you see in the far left here is we only have 150 degrees of measured phase variation as we iterate through all of those phase DAC values. But this is supposed to be a 0 to 360 degree phase shifter, so we don't expect that result. But we can see in the magnitude plot of the S21 that there is this interference pattern that is developed as we iterate through those states. So this is indicating that the leakage is coherently and incoherently interfering with the measured response of our channel that we're trying to test. So if we apply our leakage mitigation techniques, we can actually recover that full 0 to 360 degree phase wrap for the element under test. And we can see that the magnitude of that S21 plot is very flat. So it gives us good confidence that we're measuring just the one element channel in isolation from the other radiating elements in the array. And then this is the effect of that at a fully active array level, right? This is the reason why we need to calibrate. This is an example with a 256 element Ka band transmit array. Before we calibrate, we might have 30, 40 degrees or so of variation from element to element, and that causes a reduced peak gain. We have about 14.4 dB gain in this case, and the side lobes aren't symmetric, so we don't have a very good antenna pattern here. If we calibrate the array using those leakage mitigation techniques I just described, we can recover about 2.8 dB to get our peak gain up to 17.2 dB. And we can see that now the pattern has a symmetry where the side lobes are at the same level on both sides of the E-plane. And this is, again, the reason why it's important for us to calibrate. You effectively double the power in this case by ensuring that you have a good reference point for the measured phase of all your element channels after you calibrate. After you calibrate, of course, you want to know how does that affect the performance of your array, and that's what I'll describe next. So we have some test options that can fully automate pattern measurements. So this is an example of a 2D cut. The plots probably aren't very visible on the dark background, so I apologize for that. But on the left here, you can see calibrated versus uncalibrated beam patterns. The calibrated ones have the dashed lines, and we can also measure both channels on a dual linear feed for this CATR, so we can get the cross pole as well. And you can see the co-pole and cross-pole levels on the right-hand plot here. And we're collecting all of this data in a single azimuth sweep of the positioner. So at each positioner state, your array can iterate through, a dozen beam states, calibrated and uncalibrated, V-pole and H-pole, and you can gather all that data, demux it from the trace once you capture that. At the end of the measurement, we do all that data processing for you, and then you can just plot these results, and within minutes you have a 2D beam pattern that shows you your scan loss and the gain improvement when you calibrate versus when you don't calibrate, and so on. So a very valuable tool for being able to do these measurements quickly and efficiently. As I said, there's a lot more than beam patterns and S parameters when it comes to phased array characterization. So we can also look at modulation distortion if we add a vector signal generator to our test setup. So this is highlighting an example of a EVM measurement as a function of the applied RF power. And you can see the bathtub curve on the top right here. So as we increase the power, we eventually put the amplifiers and the beamformer channels into compression, and the EVM gradually increases as we increase the applied RF power. Additionally, we can apply source calibration for our vector signal generator to ensure that the source itself is not corrupting the measurement. We can apply kind of a pre-distortion to that signal under test so that when it gets sent out to our phased array port, we have a good clean signal, and then we know that we're measuring the distortion contribution of just the array under test, not also the signal generator. And that's one of the key benefits that you have in using a vector network analyzer for these measurements, is that you can apply this type of calibration. As I said, you can also do G over T, so we have some techniques to do that as well. First, you'll need to calibrate the low noise receiver on port 2 of a PNAX, for example. So we have reference standards that we can use that put out a known noise that we can use to calibrate that low noise receiver. And then once we de-embed the measured range loss, as I described before, we effectively combine a gain measurement of our array under test with a noise temperature measurement, and applying some trace math as shown on the bottom right here, we can get our G over T result over the frequency band of interest for the array under test. So we can also do G over T for receiving arrays, and as I said, for transmit arrays, modulation distortion. So there's a variety of measurement options that we have with our network analyzers. And that brings me to the final slide here. So of course, this is about the entire phased array design workflow. So we want to highlight the fact that measurement and simulation really do play complementary roles. As Mark alluded to earlier, the digital twin modeling enables you to design with confidence. It gives you kind of a sandbox for testing and tuning, trace lengths and maybe phase quantization in your phase shifters and those sorts of things, to the point that you can get a pretty accurate estimate of what your array performance should be. And then when you go and measure that, if you have a well-calibrated antenna range and you use the options that we have with our network analyzer and our software, you can quickly generate your beam patterns, your EIRP, your G over T, and then see how well it correlates with what you simulated in your digital twin model. So hopefully this will, again, ultimately save you time and money as you try to reduce the number of design iterations that are required to reach your performance requirements and meet your specifications. And also, launch these. If you're launching them on a satellite, at that point, obviously, there's nothing more you can do. So you definitely want to have high degree of confidence that your array is performing as you expect. So again, thank you for your time and attention today. And with that, I'd be happy to answer any questions you have.
I'm not familiar with the acronym SCPR. Can you just explain what that is?
Oh, Skippy, yes. So, yeah, it actually escapes me what the Skippy stands for. It's an acronym, right? Serial command. Oh, yeah. So, I couldn't remember.
Communication protocol for instruments.
Okay. Yeah. Thank you, John. So, so it's a kind of a language for sending these commands to various instruments. As I said, a good comparison is a network analyzer where you can set the frequency span or the power level. So we're developing a Skippy parser now for a generic phased array. Initially, we're supporting rectangular arrays, but we'll eventually expand that to other geometries and layouts and lattices. But this, again, provides a variety of options for you to set different beam patterns, to put your array in whatever state you'd be interested in measuring it in. So you can send a command that sets the beamformer channels, gain and phase, and there'll be some other options. A few other example commands I could show after this presentation if you'd like. Yeah, so the question was, do you have the ability to simulate end-to-end communication links, right, using the software tools, SystemVue? Yeah.
That's absolutely, yeah. But I'll just, thank you. Yeah, I would say absolutely. If you want to come over to our booth, we can show you when you have time. But just on the physical layer, end-to-end, bits in, bits out, we can do that through the uplink, downlink with like the SDK software. If you want protocol stack, that's papers are going to cover that as well with Exada. But absolutely, the answer is absolutely yes.
Given a chamber, simulate the chamber.
Simulate the chamber? Yeah, we can actually. And I can show you more if you come by. But we have over-the-air models in SystemVue, and that'll you could do like a fixed point. You could move the probe or move the antenna, but there's the ability to simulate CATR, kind of over-the-air kind of measurement in this just pure simulation. It's more accurate to bring in real measured stuff, but yes. So, I hope that answers your question. Any other questions? Yeah.
So does the SystemVue software, is it strictly RF or does it also include some DC?
Yeah, that's a great question. It's both. It has incredible RF models, and then it's got digital models as well. You don't have to buy a license of MATLAB, but it has it's called MATLAB script. So it has MATLAB in it. But yeah, it'll do bits to bits, bits in, bits out, up through the RF chain, channel, and back.
What about like DC consumption, power supplies?
Yeah, what we can do there is a lot of the models, I mentioned that they can do, you could take a data sheet for a part that has like versus frequency. It can also consume versus temperature versus bias, so you can show some effects of that. The best would be to model it in a circuit tool, like I would prefer to use ADS, but yes, we can see those effects at the system level. Thank you guys for your attention. Enjoy some coffee.